So this is a poster for the Comp 546 project and I'm going to explain it now. When we look at an object while touching it with our hand, our brain combines both cues, the vision and touch cues, to estimate the properties of that object. This paper attempts to study how that combination takes place. The hypothesis of the authors is that the nervous system uses maximum likelihood estimation to combine these inputs. So here's a sample of how MLE looks like. If this is your haptic or touch belief and it's modeled by a Gaussian, if this is your visual or seeing belief that is modeled by another Gaussian, the combined Gaussian can be given by the MLE equations which are here. So equation 1 shows the predicted mean and equation 3 shows the predicted variance of your combined Gaussian. They can be written in terms of detection thresholds in these equations, but which are expressed in these equations. But let's focus on the general idea of the paper, then the math first. The combination of the Gaussians is shown in this image. So the idea of the paper is that it determines the properties of the visual only Gaussian by doing visual only experiments. It determines the properties of the haptic only or touch only Gaussian by performing touch only experiments, and it determines the properties of the combined Gaussian by doing touch plus vision experiments. It then checks if all these three Gaussians satisfy the MLE equations. The experiment is set up in such a way that the experiment can be performed in all three modes. Haptic feedback is received here. It is obtained from feeling each ridge under the mirror, whereas visual feedback is obtained from simulated images reflected from that mirror. The task here is to compare the height of a standard ridge to a test ridge, and the response is plotted as a psychometric function of the height of the test ridge. Here's the sample psychometric function. Another thing that the paper did is it added visual noise to each of the visual inputs. In specific, it added 4 different noise levels. The use of doing this is to verify if MLE is satisfied even with varying visual noise. So let's see what happens when you add visual noise to the visual input. In general, when there's no visual noise, let's say your estimate of your vision is something like this. If the estimated height looks something like this, when you add noise, you're less certain. So the standard deviation of your Gaussian increases. So we are doing this for 4 different noise levels, which implies that we are testing this out for 4 different values of sigma v. These are the results of the vision only experiment and touch only experiment. These are the psychometric plots. You fit a cumulative Gaussian to each of these plots to get the properties of that specific Gaussian. So in this graph, you see a total of 5 lines. 4 of them represent the psychometric functions for 4 different noise levels, and you also have the haptic psychometric function. So all of these are done with only one stimulus at a time. So it's either vision only or touch only. So basically what you're getting from these experiments is the properties of the haptic Gaussian and the visual Gaussian. And then you do a similar experiment, but this time you have both vision and touch cues. So the subject is allowed to see and touch at the same time. And the psychometric functions are plotted for various noise levels again. One key insight here is that the height of the haptic input and the height of the visual input is different. So we're giving conflicting cues to the participant. This is in line with the idea that the mean of this Gaussian and this Gaussian are different. So let's call this experiment 1 and let's call this experiment 2. With experiment 1, we were able to determine the properties of the touch only and haptic only Gaussians. With the combined experiment, we were able to determine the properties of the combined experiments. Now we have to compare if they satisfy the maximum likelihood equations. So based on the results from experiment 1, you can predict the mean of the combined Gaussian and the standard deviation of the combined Gaussian. So the mean is represented here and the standard deviation is represented here. In reality, okay, why is my iPad stuck? Okay, I'm sorry for that, but where was I? So in reality, this is not actually the mean, but this is the ratio of visual heights, but this is a predictor of mean, so I'm using it for simplicity. And this is actually the threshold, which is directly proportional to standard deviation. So again, I'm using that for simplicity. And these are predicted by looking at the properties of the touch only and vision only Gaussians. But when you do experiments and find the actual mean and standard deviation, you can see that they are quite in line with our predictions. Hence, the paper says when the values of both the visual and haptic cues are quite similar, the brain performs MLE to form a combined estimate about the height of the object. Thank you.